Let's talk about section 4.6. It literally combines everything that you've learned in pre-calculus and in calculus to enable you to graph more precisely than you've ever been able to before. Let's first just go over what we can tell from the first and second derivative. If we have a function that's continuous on a closed interval from a to b, that means includes the endpoints, and differentiable on the open interval from a to b, does not include the endpoints, except for possibly at some point c. And we'll talk about why the except possibly at some point c later. Then the function of the graph can be classified as follows, where the first derivative is positive, the function's increasing on the interval. Where the first derivative is negative, the function's decreasing on the interval. Where the first derivative is 0 or undefined, then c is a critical number and f of c is a possible relative extrema. Doesn't guarantee that f of c is a relative extrema, but it's possible. The first derivative test simply says if the first derivative changes its sign at c, the function's either going from increasing to decreasing or decreasing to increasing, then f of c is a relative extrema. Where the second derivative is positive, the function is concave up on the interval. Where the second derivative is negative, the function's concave down. And when the second derivative is 0 or undefined at c, then f of c is a possible point of inflection. Point of inflection is just where the concavity changes. If the second derivative changes its sign at c, then f of c is a point of inflection. And then finally, the second derivative test tells us if we find the critical points of the first derivative, we find what makes the first derivative 0, and then we substitute it into the second derivative. Where the second derivative is positive, f of c has a relative minimum, and where the second derivative is negative, f of c is a relative maximum. If f double prime of c, if the second derivative of a function is 0 at c, then the first derivative test has to be used. Second derivative test doesn't tell you anything if your critical number of the first derivative makes the second derivative equal 0. We'll talk more about second derivative test in a minute. Remember, I said in section 4.4 that I rarely use the second derivative test. If I have to give where the function's increasing or decreasing, then I can tell if my critical numbers are relative max or min without having to find the second derivative. So I rarely use it. Just other things that we've talked about, you can drag back from pre-calculus or some sections in calculus. We've talked about the definition of a horizontal asymptote. While y equals L is a horizontal asymptote if the limit of the function is approaching L as x goes to infinity or negative infinity. So if you have a rational function, just a polynomial in the numerator, polynomial in the denominator, you can use your theorem on horizontal asymptotes for rational functions from pre-calculus. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is going to be at 0. If the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is going to be the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, there's not going to be a horizontal asymptote. Now that works fine for rational functions. For transcendental functions, you have to find the limit as x approaches infinity or the limit as x approaches negative infinity and see if there's some y value that the function is approaching as the graph goes forever to the left or to the right. And we'll do an example of that. The last thing before we get to some examples, this is also just a reminder from pre-calculus. In this number 3, we said if the degree of the numerator is greater than the degree of the denominator, then there's not going to be a horizontal asymptote. but there may be a slant asymptote. A slant asymptote is specifically when the degree of the numerator is just one more than the degree of the denominator. And if you divide the numerator by the denominator, you're going to get a linear quotient, and that quotient gives you the equation of your slant asymptote. And we'll do an example of that.
First thing I want you to do is find the domain. And I want you to write the word domain. What's the domain of a polynomial function? Negative infinity to infinity, or you could use fancy R. Either one. Number 2, find the intercepts. Actually, I could break this into an A and a B part, but I won't because I didn't on my paper. Let's find the y-intercept and then the x-intercept if it's not terrible to find. If it's terrible to find, I won't worry about it. But y-intercept's always easy to find. You just do what? Let x be 0, and I can see that would give me what? If I let all those x's be 0, everything would be gone but the 5. I don't care if you write the ordered pair 0, 5 or the number 5, as long as you graph it on the y-axis. The x-intercept, how do you find the x-intercept? I don't think I want to do that. It won't factor by grouping. There's something called the possible rational zeros theorem. Do you remember that guy? I could list my factors of 5 over my factors of 1, find my possible rational zeros. Here's my promise to you on the test. If you can't fairly easily find the x-intercept, then I won't ask you for the x-intercept. You're going to have to use the possible rational zeros theorem to find it. I just won't put that on the test. So let's not do that right now. How about that? We could do it. We don't want to do it. I think the rest of the problems that I've seen so far in 4.6, it's not so bad to find the x-intercept. You'll be able to do it. Third, I want you to find the asymptotes. Do polynomial functions have asymptotes? No. What are the only, show me with your hands, what's the only 4 things a polynomial function can do on the ends? X squared, negative x squared, negative or positive x cubed, and negative x cubed. No asymptotes. That's the only 4 things a polynomial function can look like. All right, 4 is where the work comes in. And not so much on a polynomial function, but 4 has to do with all of your calculus. You've got to find both derivatives, find what makes them 0 or an undefined, put them on a number line, determine whether they're positive and negative, and then you can answer parts A through G. So the first derivative of that function, 4x cubed minus 24x squared plus 36x minus 16. How am I going to find the critical numbers of a 3rd degree polynomial that I don't think will factor by grouping? If I factor 4x out of the first 2, that'll leave me at x minus 6. No, that's not going to factor by grouping. How can I find the critical numbers? How could I have found the x-intercepts but chose not to? I could use the rational zeros theorem. I don't think I'll have to, because if I can just find the first 0 of this, then I can use synthetic division to get it down from cubic to quadratic, and I can go from there. I can either factor further or I can use quadratic formula. I only have to find 1 0, 1 critical number before that's manageable. So how do you find 1 0? That would be helpful. Factoring out a GCF is always a good idea. Already looks a little more manageable. Oh, wouldn't that be, let's see. Oh, 4 times 6 is not 36, is it? I can do calculus, I just can't multiply. Okay. So, any suggestions about how to find a 0 or our first critical number? How about yes? And try something. If you were going to try something, what would you try first? Really? Why? You can just see. Did God whisper 4 to somebody? Yeah. Okay, 4 would not be my first thought. It might turn out to be a 0. It would not be my first thought. My first thought, well, would be, let's see if 1 works. If it doesn't work, I might try -1. And I just pray that I don't have to go too far before I find my first 0. I think, does 1 work? 1 minus 6 is -5, plus 9 is 4, 4 minus 4 is 0. So we found the first 0. Not scientifically, not methodically, but we just guessed and we tried. And I wouldn't give you one that you couldn't find that first 0 pretty quickly. So if we see that 1 is a 0 of that function, that means I can do synthetic division with 1 in the box, and I better get what for a remainder? I better get 0 for a remainder, or else I'm wrong about 1 being a 0 of that derivative. Out beside the box, those coefficients, 1, -6, 9, -4. That allows me to factor my derivative into what linear factor times what quadratic factor. I have +1 in the box, I'm dividing by x minus 1, and my quadratic factor is, which just happens to be something I can factor further. All right, so I had to use a trick, synthetic division, to get it down into something manageable. But now I can see that the derivative is this. Please check your factoring. I don't want you to make a mistake right here and the whole rest of the problem be wrong. Yes, sir. I could divide both sides by 4. When I set that equal to 0, I could either divide both sides by 4, or I could set 4 equal to 0 and say, well, that doesn't give me a solution. All right, so that derivative is x minus 1 squared times x minus 4. You don't have to write it that way. The previous line's fine too. So what are my critical numbers? 1 and what? 1 and 4. And because they are critical numbers of the first derivative, that means they're possible what? Possible relative extrema. I'm just making myself notes because I think in words. I just made my note. That's possible relative extrema. I'm going to go ahead and find the second derivative and what makes it 0 while I'm differentiating. Where would be the easiest place to take, what form of the first derivative would be the easiest place to find the second derivative? Up here. Yes, sir. Either this or that. Either one's absolutely fine. If you want to use this one, then you keep up with the 4 and you just factor this. Would be 3, not factor, differentiate. You differentiate that, would be 3x squared minus 12x plus 9. And then I'm looking for what makes that equal 0. I can factor a 3 out of that, multiply the 3 times the 4 that I already have outside. It gives me 12 times x squared minus 4x plus 3. And thankfully that will factor. So what makes the second derivative 0? 3 and 1, and those are possible what? Possible inflection points. Hey, 1 is either a relative extrema or a point of inflection. I don't know which. I'll find out which. Possible inflection point are at 1 and 3. So I'm ready to look at the sign of the derivatives. And here's how I'm going to write my number line. I'm going to find the sign of the second derivative and the sign of the first derivative all on the same number line. I'm going to put all, let's see, I had found 3 possible somethings, 1, 4, and 3. So I'm going to put 1, 3, and 4 all on that number line. If you want to make 2 separate number lines, that's absolutely okay. What's your favorite number to the left of 1? 0. Let's find the signs of the first derivative first. Here's my first derivative. I noticed that no matter what x is, this first term can't be negative. So really, I only care about the sign of the second term. Does that make sense? All right. If I let x be 0, the second term is going to be negative. If I let x be 2, the second term is going to be negative. If I let x be 3.5, the second term is going to be negative. And if I let x be 5, the sign of the second term is going to be positive. All right, let's do the same thing with the second derivative. Here's my second derivative right here. My favorite number to the left of 1 is 0. If I put 0 into the second derivative, what's going to be the sign of my answer? It's going to be a negative times a negative is a positive. What if I put in a 2? Negative times a positive is a negative. What if I put in a 3.5? Positive times positive is a positive. And what if I put in a 5? Positive times positive is positive. So now I'm looking at this because I want my parts A, B, C, D, E, F, G to match up here. A part, I want the increasing intervals. To find the intervals over which the function is increasing, do I look at the first derivative or the second derivative? First derivative, and I'm looking specifically where the first derivative is which sign? Positive, so 4 to infinity. Where's the function decreasing? Negative infinity up to 4. C is relative max. Is there anywhere that function changes from increasing to decreasing? No. It changes from decreasing to increasing, but that's a min. So there is no relative max. The relative min is going to be at 4, where the function changed from decreasing to increasing. And I'm just going to tell you that when I plugged 4 into the original function, just to save us a minute, when I plugged in a 4, I got a negative 27. That's just a minute on a calculator. And when I say when I plugged in 4, where do I mean I plugged the 4? The original function. All right, E part, where is the function concave up? What derivative should I be looking at? Second derivative, and specifically where the second derivative is positive. So it's concave up from negative infinity up into 1. And then it's positive again from 3 to infinity. Where's the function concave down? Where the second derivative is negative, and that's just 1 to 3. Is that as far as my alphabet goes? No, there's a G part, points of inflection. Are there any questions so far? Folks who are asking? Why? That a problem can take a page?
So much.
And I write very, very small, and it still takes me a page.
Yeah.
Is there an inflection point? How would I locate an inflection point by looking at that sign chart? Where the concavity changes in either direction. So the concavity changes at 1 and the concavity changes at 3. There are 2 inflection points. I would have to get the y values for them, but I have done that already. And what did I get? 1, 0, and 3, negative 16. Yes, sir. Yes, yes, it turns out we found one of the x-intercepts. It's an inflection point. All right. Step 5 is the graph. Try to get it on the same page. If I have any asymptotes, are there any questions back there, guys? Any questions? Good? Okay.
I was routing when you were talking about the inflection point.
Yes. The inflection point is where the concavity changes, and the concavity changes at 1 and at 3. Second derivative. I'm looking for something to throw at him, but I don't see anything that wouldn't hurt. I'm gonna bring you a tennis ball next time. Okay. If I had any asymptotes, I would graph those first. I don't. If I have any specific points, I will graph those next. Where are my specific points starting at the top? My y-intercept is 5. What's the next point you see? Next point I see is relative mean. Relative mean is 4, negative 27. Maybe I'll just count. Oh, shoot, I've already counted by 1s up there. I am not going to count all the way to negative 27. I'm going to draw me a tick mark way down there and label it negative 27. Which means my graph may not be to scale, but that's okay. As long as I've labeled where that is, that's okay. 4, negative 27 is a relative mean. 1, 0 is an inflection point. 3, negative 16. 3, negative 16 might be about here. 3, negative 16 is an inflection point as well. Is that all the single points that I have identified? If I just connect those 4 points, I'm going to guess this looks like x cubed. It's x to the 4th. It can't look like x cubed. So let's figure out what's going on. It's increasing from 4 to infinity. And let me check something else. It's concave. The concavity is the part that it's hard for me to work in. It's concave up from 3 to infinity and increasing from 4 to infinity. Concave up from 3 to infinity, increasing 4 to infinity. I suggest doing this in pencil, by the way. Strongly suggest doing this in pencil. It's decreasing from negative infinity to 4. So I'm not drawing this yet, but I can see that that's going to be where it's coming downhill, right there. I just got to work the concavity into that. It's concave up from 3 to infinity. I have that. Concave down from 1 to 3. How can it be concave down from 1 to 3, but yet it's decreasing? Draw what you think it would be on your paper. Concave down and decreasing from here to here. And then it's concave up from negative infinity to 1. From all the way over here to here, it's concave up. Can you make that piece look concave up? How did I think we might get 5 examples done today? I don't know. Now I'm wondering if I can get both examples that I had chosen for myself done. Gonna go for it. Any questions on this? I strongly advise you to work in pencil because there's going to be some erasing. If you don't work in pencil, then you copy over and make it neat. I don't care which one you do. I hate pencil, so I copy over and make it neat. I am not turning in chicken scratch to a professor just because I'm too lazy to recopy or work in pencil.
Number 12. Number 12 is a rational function. F of x equals x squared plus 1 over x squared minus 4. Now, how do you find the domain of a rational function? Domain's what you can let x be. You can let x be anything other than what makes the denominator 0. Now, actually, if you give me any rational function, the first thing I'm going to do is see if it will reduce. And the only way to know whether or not it will reduce is by factoring whatever will factor. That denominator factors into x plus 2, x minus 2. The numerator is the sum of 2 squares. It doesn't factor. So the domain of this function is anything except what makes the denominator 0. And in factored form, it's very easy to look at that and see the two values that make the expression 0 are -2 and +2. Now you could either write in interval notation, the domain is, I don't want to write it in interval notation. It would take too long. I'm just going to say the domain is everything not including or not equal to plus or minus 2. That is a bad looking x, but x is less than, or x is not equal to plus or minus 2 is your domain. We always find y-intercepts by letting x be 0. If we let x be 0 in that expression, we'll have 0 squared plus 1 is 1 over 0 squared minus 4 is negative 4. So the y-intercept is negative 1/4. How do you find an x-intercept for a function? Well, to find the y-intercept, you let x be 0. To find the x-intercept, you let y be 0. Now, what makes a fraction 0? The only thing that makes a fraction 0 is if the numerator is 0 and x squared plus 1 doesn't equal 0, no matter what x equals. So there is no x-intercept of this function. The vertical asymptotes are what makes the denominator 0, and we've already said that's plus or minus 2. Make sure that you write these as equations. They're not just numbers, they're vertical lines. X equals negative 2 is a vertical line, x equals positive 2 is a vertical line. Horizontal asymptotes, this is just an algebraic rational expression. We can look back at the theorem on horizontal asymptotes in our notes, but it says if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. So this horizontal asymptote is y equals 1. And again, you want to write that as an equation, not just a number. A horizontal line is y equals, and in this case, 1 is the ratio of the leading coefficients. Does this graph have a slant asymptote? Well, remember, to have a slant asymptote, the degree of the numerator has to be 1 more than the degree of the denominator, and that's just not the case here. You're not going to have both a horizontal asymptote and a slant asymptote. All right, here's where I've tried to save us a little bit of time by going ahead and finding the first derivative and the second derivative. Both of those took the quotient rule, but you should be good at quotient rule by now. So the first derivative is negative 10x over the quantity x squared minus 4 squared. And the critical values are the values for which the function is defined, but the first derivative is either not defined or 0. Now, what makes the original function, what makes the derivative undefined is what makes its denominator 0, and that's plus or minus 2. So does that mean that plus or minus 2 are critical values? No, the definition of critical value is the function has to be defined there. The function's not the function is not defined at plus or minus 2, so plus and minus 2 cannot be critical values. The critical value will only be what makes the numerator 0 in this case, and that's x equals 0. 0's the only critical value, and it's a possible relative extrema. We'll find out in a minute if it is an extrema. All right, I also found the second derivative, and the critical numbers of the second derivative are what makes its numerator or denominator equal 0. Again, plus or minus 2 cannot be critical numbers because the function's not defined there. But whatever makes the numerator 0 could be a critical number. What value of x would make that numerator 0? Well, if you set 3x squared plus 4 equal to 0, you would find out very quickly that there's no real solution to that equation. So there are no critical numbers for the second derivative, and that tells you, getting just a little bit ahead of ourselves, but the critical numbers of the second derivative, if anything, are the possible inflection points. Since there is no second derivative, there are no inflection points to this graph. Okay, we determine almost the rest of these answers by making a sign chart. And it's very important to understand that on our sign chart, we need the critical numbers of the first derivative. In this case, there were no critical numbers of the second derivative, but there's something else you need to include. We could not call 2 and -2 critical points by the definition of critical point because the function wasn't defined there, but I can call them important points. They're important enough that I need to include them on my number line. You'll see why that's important in just a second. Let's go ahead and put the -2, the 0, and the +2 on a number line. And we're going to find the sign of the first derivative and the second derivative in each of those intervals. Now the first derivative, my favorite number to the left of -2, if I put a -2 into this first derivative, I'd have a negative times a negative over a positive. That would make that whole expression positive. Likewise, when I let x be -1, I'd have a negative times a negative over a positive. That makes the first derivative positive for any negative number that you put into it. Now, if I put a +1 into the first derivative, I'd get a negative times a positive over a positive. So at +1, the first derivative would be negative, and likewise, at 3, the first derivative would also be negative. Actually, we didn't have to test all 4 intervals for the first derivative because we knew that the first derivative only changed signs at 0. That means if the first derivative is positive here, it's going to be positive here also. If it's negative here, it's going to be negative there also. What about the second derivative? If I take my test point, say -3, and put it into the numerator, actually, I can see that the numerator is always going to be positive. If you square something, triple it, and add 4, you're always going to get a positive. So I'm really only concerned about the sign of the denominator. If I let x be -3, that will become 9 minus 4 cubed, and that's a positive. If I let x be -1, that will be 3 plus 4 is positive. Oh, wait. I said the wrong thing. If I let x be -1, then, like I said, the numerator is always positive, but the denominator will become 1 minus 4, which is -3, cubed is -27. Even though -2 was not a critical number for the second derivative, the sign did change from positive to negative there. So -2 can't be an inflection point because we know there's a vertical asymptote at -2. I actually like to do that also. When -2 is a vertical asymptote and +2 are asymptotes rather than critical numbers, I like to dash them in on my number line. It helps me remember that. All right, the test point 1 into the second derivative would give me the numerator's positive, the denominator's negative, so the whole thing would be negative. And then if I substitute 3 into the second derivative, I would get a positive over a positive is positive. So I know the sign of the first and second derivative in all of the intervals that I'm concerned with. To the left of -2, between -2 and 0, between 0 and 2, and then to the right of 2. I can get the rest of this information from that graph. I can't believe I said graphed, just graph. The increasing intervals are where the first derivative is positive. And the first derivative is positive all the way up to 0, except for you couldn't say it's positive at -2 because the function's not defined at -2. So I'm going to actually have to write two separate intervals here. I'm going to say from negative infinity up to -2, not including -2, and then from 2 to infinity. Sorry, -2 to infinity. And I don't mean that. I meant the first derivative is positive from negative infinity to -2, and then from -2 up to 0. And the function is decreasing wherever the first derivative is negative. So the first derivative starts being negative at 0, and I really can't say to infinity because there's a break in the function right here, a non-removable discontinuity. So I'm going to say the function is decreasing from 0 up to 2, and then from 2 to infinity. Now another thing that I can determine from the first derivative is where there's a relative max or min. There's a relative max wherever the function stops increasing and starts decreasing. So there's a relative max at 0, and just to speed things up a bit, I went ahead and substituted 0 into the original function and got y as -1/4. You want an ordered pair so that you can graph that ordered pair later. A relative minima is where the function goes from decreasing to increasing. Is there anywhere on this graph that the first derivative was negative and then turned positive? No. So this graph has no relative minima, just a relative max. A function is concave up. How do you tell the concavity of a function? What do you look at? You look at the second derivative, and the function's concave up wherever the second derivative is positive. So that's negative infinity up to -2, and from 2 to infinity. The function's concave down wherever the second derivative is negative. So it's concave down. Is it okay to say from -2 all the way to +2 without having to break it into two intervals? Yes, the function's continuous from -2 to +2. There's no vertical asymptote or discontinuity in between those. So I can say concave down from -2 to +2. Points of inflection are my critical points of the second derivative, or where the function changes concavity. Well, the only place where the sign of the second derivative changed was at its asymptotes, and an asymptote can't be a point of inflection. We had already determined up here that there was no point of inflection. So maybe the most difficult part of this process is taking all this information and putting it on a graph. First, plot any asymptotes you have. We know that this graph has vertical asymptotes at -2 and +2, and it has a horizontal asymptote. In the E part, we found the horizontal asymptote is 1. Y equals 1. We found our first whole ordered pair at, well, let's see. We found the y-intercept to be -1/4. So that was the first ordered pair we got. And we said there are no x-intercepts. So make sure your graph doesn't cross the x-axis anywhere. The next ordered pair we got was our relative maxima, which turns out to be our y-intercept, 0, -1/4. So that's all of the ordered pairs that we have. Now we've got to get the increasing, decreasing, and concavity correct, and we want to use as few test points as possible. Anytime we're in doubt, we could use a test point, but I think we have enough information to graph this without any more specific points. To the left of -2. To the left of -2, we know the function cannot be below the horizontal asymptote, or it would have an x-intercept. It doesn't have an x-intercept. So the graph has to be above, and we have from -∞ to -2, the graph is increasing, and it's concave up. So what does increasing and concave up look like? That's what the graph looks like to the left of -2. Between -2 and 0, we said the function's also increasing, but it's concave down from -2 to 2, or concave down from -2 to 0. So how can I make a piece of this graph increasing and concave down? That's increasing, the concave down. And then from 0 to 2, the graph is decreasing and concave down. Decreasing and concave down looks like that. And then from 2 to infinity, the graph is decreasing and concave up. Decreasing and concave up. That is a pretty darn good graph of that function. We could graph it on a calculator just to be sure. On the test, you can check your graph with the calculator, but you still have to show all the work. You have to show the first and second derivative and what you did to get where the function's increasing, decreasing, the relative max and min, and the concavity and points of inflection. Let me just add one thing before we go on to the next example. Sometimes it's a little hard for me to picture decreasing and concave up. How can something be decreasing and concave up? Well, I can illustrate that. Let's see how many colors of ink I have here. I think I have 4 colors. Decreasing is going downhill from left to right. Concave up would, we say, would hold water. It actually means the slope of the tangent line is decreasing, but it's easier to say would hold water. So this piece of the graph is definitely decreasing, but it holds water because if I continued that trajectory, you could see that it would be concave up. So that little piece of the graph is decreasing and concave up. This piece of the graph is increasing and concave up. This piece of the graph is definitely decreasing And if you finished kind of a parabola there, I don't actually want to draw that. I just wanted to show you why that piece of the function is decreasing. Can't get my whiteout tape to work. This piece of the graph is decreasing because you look at it left to right and concave down. The only other thing I have is a highlighter. This graph is increasing, but once again concave down. All right. I need to get 2 more examples on here. And the next one I have is number 16. Number 16, f of x equals 4 over x squared plus 1. Now that's also a rational expression, but to get to determine what makes the numerator 0 and what makes the denominator 0 so that I can find critical numbers, I need to write that as a single rational expression. If I just multiply that 1 by x squared over x squared, then I have a common denominator and I can add the numerators. When I have a single fraction, it's easier to see the domain and what makes the numerator 0 and what makes the function undefined. Actually, the domain, you could tell here or here that x could be anything but 0. To find a y-intercept, you would let x be 0, but we just said you can't let x be 0. What does that tell you about y-intercepts? There just is no y-intercept. X-intercepts would be what makes the whole fraction 0, and what makes a fraction 0 is what makes the numerator 0. Well, there's nothing that makes that numerator 0. So there are no x-intercepts either. Vertical asymptotes are going to be what makes the function undefined or what makes the denominator 0. We've already said 0 makes the denominator 0. So x equals 0 is your vertical asymptote. Again, write it as an equation, not just a number. What about horizontal asymptotes? Well, as a rational expression, we can say if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. The leading coefficients are both 1. Leading coefficient doesn't necessarily mean the first number. It means the coefficient of the highest degree term. So the ratio of the leading coefficients would be 1. There's no slant asymptote unless the degree of the numerator is 1 more than the degree of the denominator. And now we need the derivatives. I didn't do the work on this one. We could either use the quotient rule on this, or we could use the quotient rule on our original expression. I think it would be a little easier to take the derivative of this original function because the derivative of 1 is just 0. I'm going to write that function as 4x to the negative 2. To make it easy to see, the first derivative is negative 8x to the negative 3, or negative 8 over x cubed. And I'll go ahead and find the second derivative while I'm at it, because I know I'm going to need it for concavity. The second derivative would be positive 24 x to the negative 4, or 24 over x to the 4th. So the first derivative is negative 8 over x cubed. The critical values are what makes the first derivative 0 or undefined, with the caveat that the function has to be defined there. There's nothing that makes that numerator 0. The only thing that makes the denominator 0 is 0, and the function's not defined there. So there are no critical values of the first derivative. The second derivative is 24 over x to the 4th, and it doesn't have any critical numbers either. What does no critical numbers of the first derivative tell you? Well, if there were critical numbers of the first derivative, what would they be, possibly? They would be possible relative extrema. Since there are no critical numbers, there's no relative max, and there's no relative min. Since there are no critical numbers of the second derivative, there are no points of inflection. So this graph is going to be interesting. What will we put on our sign chart if we don't have any critical points for either the first or the second derivative? Well, I mentioned this on the previous problem. Even though we can't call 0 a critical number, technically, it is an important number, and I'm going to put it on my number line and dash it in to remind me that it's not a critical number. There's a vertical asymptote at 0. And then I'm going to find the sign of each of the derivatives to the left and to the right of that vertical asymptote. If I put a negative number into the first derivative, I would have a negative over a negative is a positive. And if I put a positive number into first derivative, I'd have a negative divided by positive is a negative. How about the second derivative? If I put a negative number into the second derivative, it's positive. If I put a positive number into the second derivative, it's positive. So let's see what that tells us about where the function's increasing and where it's decreasing. It's increasing wherever the first derivative is positive. So it's increasing from negative infinity all the way up to 0, but not including 0. And it's decreasing where the first derivative is negative. So it starts decreasing at 0 and keeps increasing forever to the right. We've already said there's no relative max, there's no relative min. What about concavity? For concavity, you look at the sign of the second derivative. It would be tempting to say the second derivative is positive everywhere, but remember the second derivative doesn't exist at 0. So I'm going to have to write where the function's concave up as 2 intervals. I can't just say negative infinity to infinity because that would include 0. I'm going to have to say negative infinity up to 0, but not including 0. And then 0 to infinity. The function is not concave down anywhere because the second derivative is not negative anywhere. And there's no point of inflection because there's nowhere the second derivative changes signs. So it seems like we have very little to go on here. We don't have any ordered pair to graph at all. We didn't have a y-intercept or an x-intercept. We didn't have any critical points of the first derivative, critical points of the second derivative. We could say, try to dash in the y-axis to say that x equals 0 is a vertical asymptote. And also y equals 1 is a horizontal asymptote. We just need to graph that function so that it doesn't cross either axis, not the x-axis or the y-axis. That pretty much tells you where the graph has to be. If it can't cross the x-axis, it can't be here, it can't be there. So it has to be above the horizontal on both sides of x equals 0. Let's just be careful with our increasing, decreasing. The function's increasing everywhere. I'm sorry, that's not right. It's increasing from negative infinity to 0, and it's concave up from negative infinity to 0. So what does increasing and concave up look like? That. To the right of 0, the graph is decreasing, but still concave up. And that's the graph of 4 over x squared plus 1. Let's just double check it really quickly. On the calculator, if I entered 4 over x squared plus 1 and just set my window to standard, I can say zoom and number 6 is zoom standard. That sets my window back to negative 10 to 10. That's pretty much what our graph looks like. If I wanted to see the horizontal asymptote, then I could graph it as a second function. Let y2 be y equals 1. And there's my horizontal asymptote. The graph's getting so close to it that out past about negative 5 and positive 5, it looks like the graph just coincides with the horizontal asymptote, but actually it's getting closer and closer.
All right, number 10 is negative x squared minus 4x minus 7 over x plus 3. I want you to label number 1, domain. And before I just jump right in there, no, I can go ahead and say that the domain is everything except for what? Negative 3. And I'm pretty sure that at negative 3, what will happen? That there will be a vertical asymptote. The only way there would not be a vertical asymptote at negative 3 would be if what? If that function, if that numerator would factor in such a way that I could cancel out the x plus 3 or negative 3 would still not be in the domain of the original function because the original function had x plus 3 in the denominator. But if I could cancel out that x plus 3, then rather than having a vertical asymptote at negative 3, what would I have? A hole in the graph. You can tell that doesn't happen, that numerator is prime. All right, number 2. What about the intercepts? The y-intercept. How do you find it? Let x be 0. I can see that y would be negative 7/3. What about x-intercepts? You would have to use the quadratic formula. Without writing down the quadratic formula, tell me what goes under the radical. B squared minus 4AC. Can you tell me whether B squared minus 4AC would be positive or negative? B squared would be 16. No, yeah, B squared would be 16 minus, what would 4AC be? 28, and 16 minus 28 is negative. What does that tell you about x-intercepts? The answer you would get from the quadratic formula is an imaginary number. An imaginary number can't be an x-intercept, so there are no x-intercepts. I'm not just saying we can't find them. I'm saying there is none, because if you set that numerator equal to 0, you would only get imaginary solutions. All right, number 3. Is there a vertical asymptote? Is there? Yeah, since I can't cancel out that x plus 3 in the denominator, the vertical asymptote is x equals negative 3. Make sure you're giving me an equation, not a number. Negative 3 is not a vertical asymptote. Negative 3 is a number. X equals negative 3 is a vertical asymptote. What about horizontal asymptote? If the numerator is higher degree than the denominator, then, well, is there a horizontal? No. There's no horizontal because the degree of the numerator is higher than the degree of the denominator. But because the degree of the numerator is only 1 higher than the degree of the denominator, there's a slant asymptote. And how do I find it? If the denominator was a monomial, I would divide that into 3 terms and get the linear part. But because it's a binomial and I can use synthetic division, I'll use synthetic division with negative 3 in the box and the coefficients negative 1, negative 4, negative 7 out beside that box. Yes, sir. What did I do? I just lost my negative? Yep, you're right. Negative 3 times negative 1 is positive 3. So that's negative 1 times negative 3 is positive 3. Negative 7 plus 3 is negative 4. I will accept that much marking out on your paper. That in my book is still neat. I've seen stuff from a few people that isn't neat. So what's my slant asymptote? Y equals negative x. These are the coefficients of my quotient. Negative 1x minus 1. So I have 1 vertical asymptote and 1 slant asymptote. That's number 3. Number 4 starts the calculus. And I think, just for time's sake, just to get this problem done, I'm going to go ahead and tell you what I got for the first and second derivatives. That's what I got for the first derivative. So what are the critical numbers? Or I'm just going to go ahead and label them possible relative extrema. Where are my possible relative extrema? Negative 1, negative 5, negative 3? No, because why? Negative 3 is not in the domain of the original function. So my only two critical numbers, my only two possible relative extrema are negative 1 and negative 5. And then I'm going to tell you what I got for the second derivative. Oops. Negative 8 over x plus 3 cubed. One of those rare instances where the derivative kept getting simpler instead of uglier. Second derivative have any critical numbers? Only negative 3, and negative 3 is not in the domain of the original function. What does that tell me about inflection points? No inflection points. So I'm ready to think about the sign of the second derivative and the first derivative. What numbers do I need on my number line? You need that vertical asymptote there so you don't just skip right over it. I don't remember what section that was, 4.2 I think, said put your discontinuities and your critical numbers on a number line. So here's negative 5, negative 3, negative 1. And this is how I tell myself, hey, there's a vertical asymptote there. All right, let's find the sign of the first derivative in each interval, and then we'll find the sign of the second derivative in each interval. First derivative to the left of negative 5 is negative 6. Everybody look up for a second. I'm trying to make this as easy on myself as I can. If I realize the denominator is always positive, I'm not even going to worry about it. I'm just looking at the numerator and saying negative 6 would give me a negative times a negative times a negative, which would be a negative. I don't care what it is, I just want to know its sign. What about a negative 4? I have a negative times a positive, and that would give me a positive. What about negative 2? That would be a negative times a negative times a positive would be a. Okay, why do I have so few people talking? Have I made a mistake? Or did y'all get shy all of a sudden? Let's try this negative 2 again. Negative, negative, positive, positive. And then my favorite number to the right of negative 1 is 0. 0 would give me negative, positive, positive, which is a negative. Let's do the same thing for the second derivative. I really don't have to use 4 test points here. I can see that the second derivative is only going to change signs where? At negative 3. And so if I put in, I could use the negative 5 if I wanted to. If I put in a negative 5, I'd have a negative over a negative would give me a positive. That means positive both sides there. And then what if I put in a negative 2? I'd have a negative over a positive is a negative. So I'm ready for my alphabet. This function is increasing where? Can I say solid negative 5 to negative 1? No, because it's split up by that vertical asymptote. I have to say negative 5 to negative 3, and then from negative 3 to negative 1. And then B, it's decreasing. Where? Negative infinity to negative 5 and negative 1 to infinity. C part is relative max. Is there a relative max? Wherever the function goes from increasing to decreasing, and that's at negative 1. Negative 1, and I'll just tell you when I put negative 1 into the original function, I got negative 2 for y. Is there a relative min? Where the function goes from decreasing to increasing at negative 5. Negative 5. When I put negative 5 into the function, I got positive 6. Which brought to mind a very interesting question. How can there be a max at negative 2 and a min at 6 if 6 is bigger than negative 2? I don't get that. Hang on one second. Think about it. How is that possible? All right, tell me what you think. That's not the reason. That's not what I was thinking as the reason that your min can be higher than your max. How is that even possible? Because they're relative. That's not absolute max and absolute min, or that wouldn't make sense. But this negative 2 can be higher than what's on either side of it, and this 6 can be lower than what's on either side of it. All right, E part is concave up. Where's the function concave up? Wherever second derivative is positive, negative infinity up to negative 3. Where's the function concave down? Negative 3 to infinity, wherever the second degree is negative. Second derivative is negative. G, what's the inflection point? Is there an inflection point? No, we decided that way up here when we saw there was nothing that made the derivative 0, second derivative 0. All right. There's the actual size of my writing. Put it on a graph. I always graph my asymptotes first. I have a vertical asymptote at negative 3. And I have a slant asymptote, y equals negative x minus 1. That has a y-intercept of negative 1 and a slope down 1 to the right 1. Those aren't points on my graph. Those are points on my asymptote. And come on, straight line. Ooh. One of my better straight line days. Now, what points do we have? The y-intercept is a little below negative 2. What other points do we have? Relative max is negative 1, negative 2. Relative min is negative 5. 4, 5. Positive 6. This could be a little bit tricky without graph paper. Because I've already done it, I know that negative 5, 6 is in this part right here. That'd be much easier to do with graph paper, and precisely you could tell it's a little bit above the slant asymptote, not a little bit below. Any other points? Nope, that's all my points. So decreasing from negative infinity to negative 5, decreasing but concave up. Gotta sneeze. I never have just one. I did. Okay. Decreasing negative infinity to negative 5, but concave up to negative 3, concave up to this vertical asymptote. So decreasing, something's bugging me, decreasing, oh, negative 5's right here. It's decreasing up to that point, and then it's increasing, and it's concave up. And then from negative 3 to negative 1, it's increasing. Here's negative 1 right here. Increasing and concave down. At negative 1, there's a relative max. It starts decreasing and concave down, approaching that asymptote.
I was able to get these 4 examples done. So your homework tonight is those 4 odd problems. And if you have any questions, I'm not going to do any one of these problems as an example tomorrow. I've already done 4 examples, and they take about 10-15 minutes each. So if you have a specific question about a specific part of one of these, if you say, hey, I missed the y-intercept, or hey, I don't understand how to graph concave down and increasing, I can help you with that. But you need to try those 4 problems and only ask me very specific questions about them tomorrow. All righty, have a good day.